Okay. Yeah, and I'm sorry, I haven't finished grading your exams. I'll definitely have them done by Friday. Okay, so if people want to come by the office on Friday, maybe I'll like leave them in envelopes outside my office door, if people want to pick them up. Okay, so yeah, I teach in a humanities class as well, so I was like grading essays I'm still grading essays anyway.
What's your humanities class?
So Scripps has something called the core program in interdisciplinary humanities. It's a course that all the students have to take, and basically like a bunch of professors get together every 3 years. So and then they choose a common theme, and then each one chooses a text or something that's related to that common theme, and then they make one lecture. So like the first lecture was on this seminal text in psychotherapy. The second lecture was on, again, a sort of seminal text in media studies. Third one was on Shostakovich's Fifth Symphony. The fourth one was on like sort of like the what's it called? Suppression of ideas, basically. Like the suppression that he went through at the time, the oppression he went through at that time. And then like we read an Italian novel, we read a science fiction story, we read a book about city planning.
Did you have them read Stein?
Well, so I wasn't involved with the creation of this version of it. So no, I didn't have any say in I'm not one of the lecturers. I didn't give one of the lectures, but I'm just sort of it's sort of perennially unpopular, and nobody wants to teach in it. So but except for me, I actually like teaching in it. So I was like yeah, I'll teach in it. So I'm helping out, but I wasn't one of the creators. Yeah. In the past, I have had them. I had them read like this series of lectures, some selection from a series of lectures by Laplace on probability, because you can't really give too technical material, right? And Laplace gave a series of lectures on probability to the public, at one point, and so that's kind of like vaguely usable for them. And they said like try to find mathematical source material, but don't make it too mathematical. So, yeah. Okay. So. Yeah, and then they asked me to lecture on somebody called Condorcet. Condorcet, is anybody familiar with this name? I'd be surprised. It's he's kind of not well known, but like Robespierre. You guys know the name Robespierre. Robespierre said, like, to mathematicians, Condorcet was a man of letters, and to men of letters, Condorcet was a mathematician. Just like a burn from Robespierre. Okay, so anyway, let's get to it. So remember what we're trying to do, right? We're proving Hadamard's theorem, right? And we're trying to show that that the function g is a polynomial, right? And we've got it down to one last thing, using that lemma that said that if the real part grows like a polynomial, then the entire function must also be a polynomial. We've got it down to one estimate, right? And so this was the estimate that we needed to show that this thing was bounded from below by e to negative c z to the s, right? For z equaling ri for some sequence ri such that ri goes to infinity. Right. That was where we stopped, and we separated it into two cases. Right. It was case one where it was the roots that were large, right? So that z over a sub n was less than a half. And you remember what we showed was that, I'm going to say this again because we're going to do something similar in the second case. What we showed was that we could get this sort of bound, right? That there was we could get this sort of bound, right? And right, and what we did with that bound was that we said, well then, once we had that bound, then we said, well, when you take the product, over the a sub n such that z over a sub n is less than a half, right? You get that's you get a bound from below, of course, right? You get that this is greater than or equal to e to the negative 1/2 k minus s. You factored out the z of s, and you got left with this summation a sub n to the negative s over those guys. Right. That was right. And because of the finite growth of the function, we had shown that there was this sparsity to the roots, so that this thing was finite. Right. That's how how this estimate turns into this estimate. Right. Because then this and this we just subsume into some positive constant. Okay, and we say, okay, we got it, right? This is what we wanted, right? And that gives us that part of the lower bound. Okay, so that's where we stopped. That's where we stopped last time, and then we're going to do it for the guys where the a sub n is small. Okay, everybody know where we are? Okay, yes, Kai.
I was going to say, so like where you pick your cutoff for, like we're taking all z over an with norm less than 1/2, right? But depending on your choice of z, which an's fall into which bucket changes. Right?
Yeah.
Okay,
yeah.
but that's okay.
That's okay. Yeah.
Okay.
It'll. Yeah. So you have some z, right? You have some z for a particular size. I mean, at this point we don't even need that size.
Yeah.
Okay. But later on, but yeah. So you're gonna have some z, and then for that z, you're gonna get the bound, and the
right.
the bound doesn't depend on c. You see this bound. Depends on. I mean, this number just comes from the function, right? And this number doesn't depend on anything.
So, but the cases do depend on z. It's just if we have the bound for each case. Then,
Yeah.
okay,
Yeah.
I understand.
Yeah. Okay. Okay. So now we'll do it for the other side, and that turns out to be more complicated. Okay. So case 2. Case 2, the a sub n such that z over a sub n is greater than a half. You say, okay, well, just by definition, this thing is, of course, 1 minus z over a sub n times e to the it's okay. Right, yeah, sorry. Yeah. Times e to the summation z over a sub n to the j over j as j goes from 1 to k. Okay, so we're just going to look at these factors. Okay, so consider this guy here. As before, we play the absolute value of e to the w is greater than or equal to e to the negative absolute value of w. So this is going to be greater than or equal to e to the absolute value of this right, and same as last time we do the triangle inequality. This is going to be greater than the sum of the absolute values, negative the sum of the absolute values. So just standard stuff that we've done before. Okay, so now think. So we do sort of like a side calculation here. So notice that for z bigger than a half, if we look at if we look at z plus z squared over 2 plus z to the k over k, that's the same thing as if we factor out a z to the k here, right? That's going to be 1 over z to the k minus 1 plus blah, blah, blah. 1 over 2 z to the k minus 2 plus 1 over k z to the k minus k. Right, so we're just factoring out this z to the k, okay, which is going to be less than or equal to z to the k. Now, z is smaller than z is greater than a half. So this thing is going to be less than or equal to 2 to the k minus 1, right? We get this 2 to the k minus 2 over 2 plus 2 to the k minus k over k. Right? Okay, nothing fancy. Right? if we ignore the denominators, right? This is just a geometric progression of powers of 2, right? Geometric sum, it's 1 plus 2 plus blah 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 up to 2 to the k minus 1, right? So that's controlled by 2 to the k. Right, of course. Right. So right, so we get this is less than or equal to 2 to the k, z to the k. Right. Okay. So now using that, coming back over here and using that, is that okay?
Yes.
Okay, great. Coming back here, we see that that this is going to give us if we look at yeah. So what do we get? We get that this is greater than or equal to e to the negative 2 to the k z over a sub n to the k. Right? I'm just using exactly that boundary there. Okay. So which is strictly bigger than e to the negative 2 to the k z over a sub n to the s. Okay. So this is again we're going to get we do exactly this is pretty much the same kind of result we got last time, right? So we do exactly the same trick, right? We say, well, look, we're going to we get that this is for these guys this is going to be greater than or equal to product e to the negative 2 to the k z of s over a sub n, right? And then we just do exactly the same thing we did last time, right? We write this as equals, right? So we get e to the negative 2 to the k zs, and then again we get that sum. We get that sum, right? This is finite. This is some constant, and so that this thing we get our constant e to the negative c to the s. Any questions? Yes, Noah.
Shouldn't whether z over n to the k is greater than or less than z over n to the s depend on whether z over n is greater than 1 or less than 1? Whereas here we only know that it's greater than a half, which wouldn't tell us that.
Yes, that would work.
I feel like
We probably just need to make
fixed
it.
if we make it true to the s.
Oh, I was just going to say just add a factor of. Yeah. We're only off by a constant factor.
So
Say
we need to
I think
multiply
you were
by
saying-
2 of the s.
Yeah.
Yeah. Okay. Yes. Thank you. So
I think Noah's saying if z over a n is 1/2, right? Then raising the power of that is actually decreasing it.
Right. Whereas certainly 2 times z over n would be greater than or equal to 1, so raising it to a higher power would result in it increasing, and then the sum, or then the exponential would decrease.
Okay, so so what okay. Right, because we're increasing the power. That makes it. That could make it smaller. Right, we're making it negative, so it goes the wrong way.
Yeah. We think this is fine because if you instead consider not just the power of z over an, but if you consider like the quantity 2 times z over an, right? That thing is surely bounded below by 1. So we can raise the power of quantity 2 times z over an.
Okay.
Or equivalently, if in the last row, if you had minus 2 to the s, I think this is fine.
Okay, so you're saying throw in a 2 here, right? Throw in a 2 here, but also divide up by a 2.
Yeah.
That would
Right.
yeah.
And then so this becomes a 1, right? And then
Yeah. We only
Yeah.
need to replace the k and the exponent with an s. That's all.
okay.
Yeah.
Okay. Thank
Should
you.
only be off by constant.
Okay, thank you. Okay. 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 Any other corrections? Thanks. Yeah, I think it actually is that way in Jerry's notes, and I thought I didn't realize why. Thanks. Okay, so that gives us control over the terms with the exponent. Now we have to get control over the term over the non-exponential terms. Okay, so now so at this point it suffices to show that if we take these terms then we can get a bound from below. Get the same sort of bound from below. So this is now the last thing we have to do. Okay, so okay, and so this is the point where we have to introduce the R sub i's. Okay, so we impose the constraint on the size of R now. Here. So, and here's what we do. We say, well, for each a sub n, let b sub n be the disk centered at a sub n with radius 1 over a sub n to the k plus 1. Okay. And now we're going to show that we can get the bound. We can get this bound for any for any z that's not in the union of the b's. So you take the union of all these disks and look at points outside of it, and we can get the control that we want there. So this is not anything too deep. You say, well, look, since the distance from z to a sub n is guaranteed to be greater than 1 over a sub n to the k plus 1. Well, then, if you look at this term that we're interested in, 1 minus z over a sub n, you can rewrite that as z minus a sub n over a sub n. Right, but that's going to be greater than 1 over absolute value of a sub n to the k plus 2, right? Because you've got this bound on the top, right, and then divided by a sub n, right? Because of the constraint, you know that 1 over a sub n is bigger than 1 over twice the size of z, right? So this is greater than or equal to 1 over twice the size of z to the k plus 2. Right. So you get this initial bound. Okay. So now recall that the number of zeros in the disk of radius r is controlled by CR to the rho, right? Where rho is the order of your function. Okay. Right. So rho was here, k was some number, and we chose s, recall, to be trapped between rho and k plus 1. Okay. So now choose an epsilon small enough such that rho is smaller than s minus epsilon. Right? So you just choose an epsilon small enough that s minus epsilon is still bigger than rho. Okay. Then, of course, n sub r is less than or equal to CR to the s minus epsilon for large enough r. Okay, so now we can those two things together will allow us to get the bound. So let's see it. So then 1 minus z over a sub n, this thing is bounded below by 1 over 2z to the k plus 2, right? And you say, like, how many factors are there of this size? Well, the a sub n are contained in the disk of size twice the size of z, right? That's what this says, right? So how many of them are there? Well, there's going to be just the number of zeros in the disk of size 2z, right? Because you're multiplying these factors, a certain number of times, just the number of zeros that are inside this disk, right? So you're taking these factors and you're multiplying them that number of times. Okay. So right, but we know that we have this bound, we have this bound on the number of zeros, right? So that gives us that this is bounded below by 1 over 2z k plus 2 quantity to some constant z to the s minus epsilon. Nope. Something wrong? Question? No? Okay, good. Okay, so, right, yeah, so, and I'm gonna, so that's gonna be, right, 2z to the negative, right, to the negative k plus 2 z z s minus epsilon. Right? That's the same thing. Well, no. Sorry. The 2 should be somewhere else. But... And I'm just gonna write it like this. 2z to some constant z to the s minus epsilon. Okay, so that I'm gonna rewrite as e to the negative c z to the s minus epsilon natural log 2z right, but that's bounded below by e to the negative c z to the s for a different c maybe, right? Because here you have this z to some power times natural log of z. But that's going to grow slow. That's going to grow slower than z to the s. Right. So it's just going to get small. It's going to get smaller. Okay. Yeah. Ty.
From the second step to the third step, on the bottom left. So when we're substituting the number of roots with our upper bound for the number of roots,
yeah,
don't we need to ensure that the thing in parentheses has like norm less than or equal to 1? Do we know this for some reason? Or is it okay to just consider, z with norm bigger than 1?
I think that's okay because we just need to show that it's bounded by that exponential. We could just multiply that. We just need to show that it's bounded by e to the negative c magnitude of z to the s, and we can just multiply by that by some constant to deal with the things where magnitude of z is less than 1.
So I say
oh wait, no, that might not be true.
there might be an easy fix in the case it doesn't work. I was just okay.
Sorry, let me. I guess maybe I haven't thought about it carefully enough. Sorry, let me go home and make sure that. I'll get back to this. I'll come back to this next time and I'll try and fix it. I'm sorry for. This is roughly right, but
no, I get the
but yeah, I guess I didn't think about all the details. I must have missed some of the details. Okay, so that's sorry about that. Yeah, that's not how I wanted Hadamard's theorem to end, but I'll come back to it. I'll definitely get it. Yeah. So. Yeah, sorry, I thought I had worked out all the details, but I guess I didn't. Okay. Yeah, I don't know if I should. So okay, let me just give the last part of Hadamard, which is so like the last part of Hadamard is that you have to is to obtain obtain the R sub I. Okay, so right, that we needed to show that the bound was true on certain radii that went up to infinity. Okay, so what you do, the way you do that, right? And we saw that the second bound holds as long as you're outside of those disks, right? So the B sub n were the disks center of A sub n, right? And so what you do is you say, well, every time you have a disk, create an annulus by rotating that disk around the origin. Okay, so this is my B sub n. I'm going to call this thing A sub n. Okay. So and then let the intersection with the real axis, with the positive real axis, be called I sub n. Okay, so then since the sum of 1 over A sub n to the k plus 1 is smaller than infinity, you know that after some point you can make this as small as you like. So there exists an n such that the sum of these things past that point, right? So n greater than n is smaller than 1/10. Okay, so then for right, so so you create a disk that so take an L that's bigger than the maximum of all the A sub n's. Maybe I should say like 2 A sub n's, just to be safe. 2 A sub n's for n less than or equal to n, right? So that everything outside of this like if we let L be here, right? The stuff that's outside of there, you know, is going to be small, right? Okay. The sums of the I sub n's are going to be small, right? The sums of the lengths of the I sub n's are going to be small outside there, right? So in that case, then L plus 1, you know, can't be covered by the union of the I sub n, right? Because the only stuff the only I sub n's that are outside of here, sum to a size that's smaller than a tenth, right? So, you can't cover the entire, you can't cover the entire interval, right? So choose, R sub L to be, anything in that interval that's not covered by the I sub n, and so so the disk of radius R sub L doesn't intersect any of the B sub n's. Okay, right, and so the estimates is going to hold. Estimate is going to hold for those R sub L's. Okay, and so the estimate holds. Yeah, right. That's what you wanted.
And R sub L goes to infinity?
Well, yeah, because you can just keep on choosing. So yeah, just choose more R sub L's, right? Take maybe I should say like take all the L's, take all the natural numbers L, that are bigger than this. Right.
I see.
Then each one of those is going to have some point that doesn't intersect the i's, and so each of those intervals, right, from your first guy onwards, right, you're gonna have some R sub L, you're gonna have some R L sub 1, R L plus 1, R L plus 2, and so on and so forth. Right?
Okay, got it.
Going up to infinity. Okay. So okay. Sorry about the. I will come back and fix that the next time. Whatever. Yeah. Okay. So okay. So now let's go on to chapter 6. Chapter 6 is about the gamma and zeta functions. So this stuff is a lot more straightforward than a Hadamard. It's a lot simpler than it's a lot simpler than the Hadamard. Okay, so here we go. So these are functions that show up. The gamma function shows up in analysis in many places, and then the zeta function, is very important in number theory. So yeah, I had hoped that we would get to the prime number theorem, but there's no way we're going to do it. I might try and make up some lectures over the break so you guys can watch. You guys can see the proof of that. Yeah. Okay. Okay. So gamma function. So, how many of you have seen the gamma function before? Some of you. Okay. So maybe not everybody. Okay. So. When you see the gamma function defined in a real analysis course, this is usually how it's defined. Right, and you don't really talk about it after this definition. You define it as this integral, the integral from 0 to infinity, e to the negative t, t to the s minus 1 dt. Okay. Okay. So. Right, for s greater than 0, but for us, we're gonna make this definition on the complex half plane. So we're gonna say this is actually for S complex where the real part of S is greater than 0. Okay. So the first thing to wonder is, does this integral even make sense? And the point is that, well, notice that if you have t to the z minus, sorry, if you have e to the negative t, t to the z minus 1, well, that's controlled by, for t bigger than 0, right? This part is smaller than 1, and this part equals t to the real part of z minus 1. Maybe I should say s, because we're using s. Right, and so we're bigger, right. So that gives you that this integral converges at t equals 0. Right. Right, and then for t large, you say, well, t to the s minus 1 times e to the negative t. Well, again, that's t to the real part of s minus 1 e to the negative t. But that's dominated by e to the t over 2 times e to the negative t, which is e to the negative t over 2. Right, and so that goes to 0. That goes to 0 very quickly as t goes to infinity, and so this thing converges on the opposite end. Right, so you get convergence near 0, and you have convergence as you go to infinity. Okay, so this actually does make sense on the right half plane. Okay, so what we want to show now is that this thing is actually analytic on the right half plane. Okay, so what we're going to do is show that it converge, that it's analytic on a strip. So let S sub delta M be this strip in the plane. So delta and M are positive numbers. Okay, and we let this thing be S delta M. Okay, and then we'll show that the thing is analytic in the strip, and the strip is arbitrary, so we can say it's true on the whole plane. So what we do is we say, well, for each epsilon greater than 0, let epsilon s be the integral from epsilon to 1 over epsilon. So you truncate the integral for the gamma function. Okay. And then what we have to do is show that this thing converges to the gamma function uniformly, right? So the gamma function is going to be the limit of these guys as e goes to 0. right? And so, so by the usual theorem, each of these guys is holomorphic. Is holomorphic in this strip. And so all we have to do is show that we have uniform convergence. Okay. So suffices to show that that these guys converge uniformly to the gamma function. Okay, so so let's look at the difference between the gamma function and this thing, right? That's going to be controlled by the part that's between 0 and epsilon, and the part that's between 1 over epsilon and infinity. Right. Now, that first part, right, for epsilon, I'm sorry, for t small, right, this thing is basically 1, right? Right. So what we get is, something basic. What we basically get is this. Right. We get t to the s minus 1 dt. Sorry, absolute value of that. Right, because s is a complex number. Okay. That is going to be t to the real part of s over the real part of s between 0 and epsilon, right? But that's e to the real part of s over the real part of s. I'm sorry, epsilon to the real part of s over the real part of s, right? But the real part of s is in the strip, so it's trapped between the real part of s is smaller than m, and it's bigger than delta, right? So we get this sort of bound, right? And then as epsilon goes to 0, this thing is controlled uniformly in terms of epsilon. This thing goes to 0 as epsilon goes to 0. Okay, and then we have to deal with the second part. Well, the second part is actually easier. So if we look at the integral 1 over epsilon to infinity, e to the negative t, t to the s minus 1. Right, that's controlled by the absolute value of that. So we get e to the negative t, t to the real part of s minus 1 dt. Right, but again, the real part is smaller than m, so this is bounded above by this t to the m minus 1 dt. Right, but this is just a polynomial, so we can control it, right? We can control it by e to the t over 2, right? Because it's just a polynomial. Right? And so we get some constant, whatever epsilon, e to the negative t over 2 to t, right? But that also is going to go to 0 as epsilon goes to 0. Okay, so what's the point? The point is that right, that these guys converge uniformly to the gamma function, right? Right. The difference between these two things doesn't depend on s. Doesn't depend on s, right? It only depends on epsilon, and so you've got uniform convergence, right? Uniform convergence of holomorphic functions gives you the holomorphic function, right? And so the gamma function is holomorphic. Okay, thank you. Okay, so yeah, I guess this is nowhere near as exciting as the last stuff, okay. Okay, everybody okay with that? Okay. Okay. Next thing we're going to do is what's called the functional equation for the gamma function. So it's that that gamma of s plus 1 equals s times gamma of s for all s in our right half plane. So note, of course, that since gamma of 1 is just 1, this tells you that gamma of n plus 1 is n factorial. Okay, so gamma function is some sort of like continuous version of the continuous version of the factorial function. That we actually extend to the right half plane, and then ultimately to the entire complex plane. So what we'll see is that the gamma function can be extended as a meromorphic function to the entire to the complex plane with poles with some poles at the negative integers. Okay, so yeah, kind of a nice formula. The proof is actually completely trivial. You say, well, it's just a calculation. You say, consider the integral of the derivative of e to the negative t to the t to the s dt. Okay. By the fundamental theorem of calculus, right, that's just going to be e to the negative t to the s, t to the s between t and between epsilon, 1 over epsilon and epsilon, right? Just by fundamental theorem of calculus. On the other side, if you work it out, you get the integral from epsilon to 1 over epsilon of s e. You just do the product rule. Right, so you just take the derivative, and write it out. But if we break that up, that's e to the negative t, t to the s minus 1 dt minus e to the negative s, e to the negative t, t to the s dt. Then, if you take the limit, let epsilon go to 0, this thing on the left turns to 0, right? And we get 0 equals, well, this is s times the gamma function, right? This is s times the gamma function, and then this thing is the gamma function evaluated at s plus 1. And so that gives you the functional equation.
Why does the left side go to 0?
Well, right, you're going to get so
Oh, I see. The exponential goes to minus infinity.
right,
And then t evaluated at 0.
right, and then as t gets right as this thing gets large, you get you get e to a large negative number, so that thing vanishes,
Yeah.
right? And then on the other side, when t is equal to 0, that's also going to be 0. Yeah. Okay. Okay. So, okay, let me try to get one more thing in here, which is extending the gamma function to the complex plane. Okay. So theorem, gamma can be extended to a meromorphic function on complex plane with simple poles at 0, -1, -2, etc., with residues with residue -1 to the n over n factorial at s equals negative n. Excuse me. Okay, so this is kind of fun. Basically, what we do is we're going to sort of like bootstrap the definition over like one step at a time. So one unit over at a time. So you say, well, right, we have it defined already on the right half plane. So if we want to extend it to, we try to extend it, one step over. Okay, and the way we do it is we say, well, we define f1 of s as gamma s plus 1 over s. Okay, so we shift everything over and we divide by s. We translate it over, divide by s. Right, the gamma function is holomorphic on on this space here. So this guy is going to be holomorphic on this on real part greater than -1, but it's going to have a pole at 0, right? So right, so you notice that f1 is holomorphic on this real part of s is greater than -1 with a simple pole at s equals 0. right? And since gamma of 0 plus 1 is just 1, we know that the residue is 1. Right? Because in order to find the residue, we just multiply by s and then take the limit as s goes to 0. Right? So we're just going to get gamma of 1, which is 1. Okay. So we created this function, right? It's holomorphic here. It's got a pole at 0, and you notice that if you're on the right half plane, where the real part is greater than 0, you get that. By definition, f1 of s is gamma s plus 1 over s. But we know that gamma s plus 1 is just s times gamma s by the functional equation. So we end up with gamma s. Right? The functional equation holds on that right half plane. Right? So we can invoke the functional equation and say, okay, this is just going to be s gamma s, and that gives us gamma of s. Okay. So what's the point? That the point is that this actually is an extension of the gamma function, right? It agrees with the gamma function over here. It's a holomorphic function that agrees with the gamma function where the gamma function was defined. And then basically you just keep on stepping one step over at a time, and extending the function in that way. Right, you can guess what's going to happen, right? F2s is going to be f1s divided by s, right? But f1s is, I'm sorry, this should be like,
f1 of s plus 1?
Yeah, sorry, f1 of s plus 1, thank you. Yeah, right, and so you end up with gamma of s plus 2 over s plus 1 times s, right, and so on and so forth. Right, so what you end up with is fms is going to be, in terms of gamma, it's gamma s plus m divided by s plus m minus 1, s plus m minus 2, all the way down to s. Okay, and that will be holomorphic on where this is greater than negative m, and it'll have simple poles at 0, -1, -2, up to negative m minus 1, negative m plus 1, excuse me. Right, and then when you calculate the residues, you take the limit of s minus minus n. So take the limit as residues at the point negative n. You take the limit of this thing times this, right? And what you get is negative n plus m minus 1 factorial divided by negative m plus m minus 1 factorial, and then you get like negative 1, negative 2, all the way down to negative n. So the top part comes from the functional equation, right? This is right, as when s goes to negative n, you know, the functional equation is going to give you this thing, right? And then on the bottom, right, as s goes to negative n, right, this is going to be negative n plus m minus 1, all the way down to negative n, right? So that's this thing. It's kind of in the middle. There's a negative n minus n, right? So there's a 0 on the top that cancels off the 0 on the bottom, right? And then, so you end up with this, that is to say, you know, negative 1 to the n over n factorial. So that's the residue. Those are the residues at the poles. Okay, that's it. Okay, see you guys next time. So next time we'll talk about the reciprocal of the gamma function, and then we'll get on to the zeta function.
So is the flow